Okay. Good afternoon. My name is Masha Demyanenko. I'm a member of the Russian MIPT team. Today I will tell you about my solution to 14th problem, solar cell characterizer. Okay, let me start. The main problem statement: propose and implement a method to determine the radiance and color temperature of light source by using solar cell materials and get accuracy, limitations, and relevant parameters, our methods. Now I want to show history line of my presentation. Necessary prerequisites, application conditions, and I realized three methods for measuring color temperature and irradiances. For the first method, I taken photodetector, this photodetector, incandescent lamp, and 3 light filters. The first method has 4 main points: confirmation of linearity mode of photodetector, measuring spectral response of our photodetector, and transmission functions of light filters. And measuring by photocells with light filters and the second method is photos of spectrum of a lamp for understanding how it is close to the spectrum of the black body. The third method with only a couple of detectors with different spectral responses. Okay, the necessary prerequisites. Emission spectrum of black body is Planck's law. The emission spectral density is power per radiation power per unit source area in a single platform located perpendicular to the chosen direction at an elementary solid angle in the wavelength range. The color temperature is the temperature of the black body. Radiation has the same ratio of the emission spectral density to selected wavelength in the observed spectrum. Application conditions. The observed spectrum should be continuous emission spectra, should be for measuring color temperature, and should be absolutely black body or uniformly gray bodies for measuring the radiances in our methods. Measurements are carried out in the visible wavelength range. For this range, work Wien's approximation. Color temperature is calculated by using this equation, by definition. The first point of second method, linearity mode of our detector. You can see logarithm voltage on the photocell on power on the lamp. It's a spectral response of our silicon polycrystalline photodetector. This is set up for this experiment. Transmission functions of light filters for this method. I taken best photometric standard for astrophysics, blue and visual, and conduct this experiment. I can get candidates for filter visual. I choose spectrum ZS2 because has narrower wavelength range. The candidate for visual blue, I choose SS5 because SS5 I able to continue because I have passport to the filter. This continue in MATLAB program. I must calculate the integral total efficiency. It is integral red curve. Because voltage on the photocell, it is wavelength integral, intensity, and transmission functions, and spectral response. Okay, you can see this value integral. I make a confirmation that emission intensity is constant on value range our transversal functions, and I get this relation, this equation. I conduct experiment with 3 filters because also I use SZS21. It cuts off the infrared range because the lamp has a maximum of the infrared range. Because therefore emission spectral density is constant on this value range, I can get this final formula for color temperature. In the second method, I get grayness coefficient. Stefan Boltzmann law, you can see, and I get for the spectrum for using a monochromator and slightly slope coefficient. It is alpha coefficient. Alpha coefficient is surface and constant Stefan Boltzmann. This coefficient see us how this source seems to black body. You can see comparison color temperature in the first method and in the second method. It's irradiance for 2 methods. For 6 points because I have difference power on our photocell or on our incandescent lamp. The third method is uses only 2 photodetectors without light filters. This setup you can see here. I get voltage ratio on temperature, on radiation temperature, and I conduct experiments. I get voltage ratio on our photodetectors, and I get temperature. Okay. Conclusions. I get irradiances, temperature, Ayres estimation in appendix. For the first method, for the second method, for the third method, I get results. And with comparison 3 methods. It's in problem statement. The reference I used in this presentation. Thank you for your attention. Questions and answers. Okay.
So we can move on then.
Okay, so thank you for your presentation. So my name is Ahmed from Team Australia. I'm going to be presenting my opposition to this problem. So to begin with, just have a list of positives and negatives about the reporter's presentation and the answer to the problem. So I think the problem was analyzed in sufficiently great depth, given that there was a systematic solution using a variety of methods. Seems to suggest that the reporter did investigate the problem correctly in a variety of manners. So the theoretical background behind some of the concepts were clearly put up there and somewhat explained on the board. And the next point here is that the reporter also happened to present their solution using a great amount of experimental data and procedures, which is good. However, on the other end of the spectrum, with the negatives, I think that the experimental setup for the experiment could have been explained in greater details. So it was clear that the reporter had completed many different experiments in many different ways. The diagrams that were shown on the presentation were not clearly explained, and the quantities being measured in each experiment were not also clearly explained. So in terms of the final answer to the problem, there was a huge table comparing the answers from all of the 3 different methods that were explored. So one of the points that I noticed was that there was no definitive answer in a way. There was the comparison and the contrast between all of the different results from the various methods, as well as the uncertainties and the limitations of each model. So in terms of theory, a lot of the terms and again, a lot of the equations, the terms were not clearly explained in the presentation. Again, they were just sort of glossed over in this case, which is something that should have been, essentially there should have been more attention put onto the theory in this case. And another point that I wanted to raise was that I believe it should have been a lot better if the experimental results were also compared to the theoretical models. So in this case, I saw a lot of graphs, a lot of presentation of the results, whether or not those were actually compared to theoretical curves, how far off the values of, essentially in terms of like up to certain constants and whatnot, how far off the values of these measurements were compared to the theory. So I'd like to essentially move on the discussion of this problem further by, first of all, having a couple of questions. The first being whether or not the Boyne's approximation using the first method is accurate. Secondly, I'd like to again ask about the comparison between the theoretical model and the experimental results, whether or not these actually fit. Lastly, whether or not the final table, including all of the results of all of the 3 different methods, could be explained in a slightly greater depth. Essentially, the solution to the problem should include a certain definitive way. And another thing which we noticed, which is also related to the same issue, is that all of the different solutions to the problem seem to be limited by the same parameters. So another point of discussion is as to why this is the case, whether or not there is any other interplay between these parameters. And also one final question on the resolution and the accuracy of data measured, and whether or not what kind of techniques, what kind of instrumentation was used to make these measurements. So yeah, that's all.
So, we get on to the discussion.
Okay, let's discuss which just
So yeah, just perhaps let's start from the top, going bottom.
comparison of theoretical models and experiment results. What are theoretical models and theoretical results, theoretical curves you mean?
So for example, whether or not you measure the spectral response or some kind of measure of efficiency of the thing that you're using, whether or not you have any kind of essentially a theoretical expression for what that efficiency should be, let's say as a function of frequency or the wavelength of the light. So whether or not you have such experiments and whether or not those actually matched what you were measuring.
I have just photodetector, polycrystalline silicon photodetector. For this photodetector has many passports in internet, in another place, but our data in experiment of measuring spectral response very correctly with compare with passports curves and curves in books in official
Okay.
sites, and you can see in passport with
Yeah,
all
so
silicon
for,
polycrystalline photodetector.
yeah, so for example, let's say that you had these panels that you were using, whether or not, depending on the frequency or like, depending on what kind of blackbody spectrum is actually hitting that solar cell or photodetector or whatever else you have, let's say, do you have some kind of theoretical expression for what the efficiency should be? Also, feel free to plug in your laptop if you want to.
Okay, I can see appendix to my presentation. Firstly, I have theoretical curves of gradation coefficient of our lamp, tungsten incandescent lamp. It's this graph. It's this graph. And we have alpha coefficient, grayness coefficient, and it's correlated with this curve.
Yeah.
So you can see it's correlated, but then curve is normalized. We have constant Boltzmann and area, the radiant surface incandescent lamp, tungsten.
Okay, yeah. So, yes. So going back to the final slide where you had essentially the results of your experimentation all tabulated. Next one, I think. The last slide. Yeah, the table here. Okay, yeah. So in this case, you've got the limitations here. Again, all three different methods using the same.
Color temperature, by definition, correctly determined for black body. Its definition for color temperature correctly determined. I mean is that is equal radiation temperature and is equal effective temperature. It is different temperature and is equal only for black body.
So in this case, did you conduct 3 different experiments using? So if you conducted 3 different experiments, then in that case, what parameter relates to each of the experiments in that case? Are they in a way, are they all the same, or is there some variation between the methods?
We have different setup, different mean 3 methods, but all methods have the same application condition because definition color temperature because is theoretical information in books on astrophysics and it's true. It's
yeah. Okay. Thank you.
Thank you.
So thank you for your presentation. I would like first to remind the subject. So the subject asked to determine the color temperature and irradiance of the light source by using solar cell materials. And they asked specifically about the accuracy of the method and the limitation of the method and the parameters. So to sum up the presentation of the reporter reminds us of theoretical considerations of black bodies, Planck's spectral radiance, color temperature, and definition of irradiance. And they proposed 3 methods, filters and photodetector. The second one was I found hard to understand. The third one used 2 photodetectors and used the relative current of the temperatures to get the relative current to get the temperature. They also considered non-ideal black bodies, so introducing gray bodies and non-ideality coefficients, and also compared quantitatively their model. However, I found that as from a clarity point of view, the presentation was hard to understand. Maybe it's a bit is due to the projector, but also the graphs were hard to understand what were on the axis. It was also difficult to follow the equations, especially when there is no commentary on them. It's also unclear if in the first method the photodetector material is indeed made of the same materials as solar cells. And also, most importantly, they mentioned, I found too briefly, the two main aspects of the question, which are the precision and the limitation of the method. And also they proposed three methods, which is good for variety, but we didn't understand which one was the best for what case. And these weaknesses were also pointed out by the opponent. They also pointed out the lack of theory, the lack of comparison between theory and experiments, how it was difficult to follow certain parts of the presentation, and the lack of definitive answer to the problem. And from the opponent, I would have maybe liked a quick summary of the key physical points that the solution of the reporter uses for their methods. So, as for the discussion, they discussed 3 points. So, agreement, what the reporter mentioned in his presentation. So, I'd like to go back to the question and focus on the 3 last points of the question, the precision limitation. So, first, I'd like to start to ask the reporter for the precision of the methods. What are the parameters? Which method is the best?
Okay, let me start. I want to discuss best method. In problem statement, talk as we must use solar cell materials. If I must solar cell materials, the best method is third method, because I have only couple of photodetector. But if you talk about accuracy of method, I choose the first method, because this method show us the minimal of errors. I want to see errors of estimate of my errors 2-3 method. You can see that the first method it's very accuracy. You can tell the second method have the minimal errors, but the second method get effective temperature. Effective temperature, don't color temperature, and in problem statement, talk nam color temperature. Get nam.
Sorry to cut. I would like the opinion of the opponent about what you just said. Do you agree that what is the difference between?
So I see that there is some uncertainty analysis here, that there are some estimated errors. My question is again, because these are sort of, let's say, starting with the expression up the top, which is essentially the spectral. Sorry, is this the efficiency or the spectral response? In this case, delta eta. What does
E emission spectral density. So what's your question?
Like, what does eta represent in this case? What is this error that you're estimating is in? Is this a change? Is this an error in
it's
irradiance, the temperature?
It is systematical errors, and it's very small errors. These errors of
sorry to cut, but it's possible
method.
to move on to the next point, because I think it's hard to understand it also.
Yeah.
But what about the limitations of our?
Sorry, big information. I want you see normal this information, but I.
Yeah, I think that the main point again here is that I think clearly you've done the experiments. Clearly, I feel like you've essentially solved the problem. It's just that the presentation of the results here is just too condensed. There's too much information for us to essentially grasp in 10 minutes. That's why I feel like
it's very interesting. It's very interesting topic. I love astrophysics. I very enjoy this problem.
Yeah.
Maybe it's hard to understand the details of your reasoning about the errors. Maybe you can talk about the limitations qualitatively, the key points.
Okay, limitations. We have chromium silicon photodetector and silicon photodetector spectral response situated in visible wavelength range. We can get main parts of energy in visible wavelength range. What?
Yeah. So in this case, like you've set up the experiment with a photocell. So did you use something similar to these, or did you use like a smaller photodetector, essentially?
We use smaller photodetector, very smaller photodetector. These errors we estimated too, and these photodetectors, it's very small, special, expensive photodetectors. In the gallium arsenidum, its photodetector can work only on the modulated frequency signal, and we use chopper. It's very important, and it's very expensive. It's very nice.
Yeah. So then going back again to the point of the question, which was, let's say that you wanted to use a solar cell. In that case, would these photodetectors be essentially, would the response be similar to a big array of cells in this case?
You can see this photodetector, this small photodetector. We focus on this photodetector. It's very difficult. In the gallium arsenidum has surface 2 on 2 millimeters on.
Okay.
And would this surface be a parameter, in your opinion, about the? Is it a relevant parameter to the problem? The surface of the detector?
I think that relevant parameters in this problem is spectral response of our photodetectors. And if you are using light filters, it is important to measuring transmission function light filters, because these parameters get us more accuracy, less errors.
What does the opponent think about the importance of the spectral response? Is it one of the most important parameters?
Yeah, so essentially I believe that the efficiency of the spectral response of the material used is essentially the main driving thing in this case, and that is not the problem. So in this case, essentially what I think is that how do you make the jump from going from photodetectors to essentially like larger solar cells, and whether or not what kind of parameters from the solar cell itself. So for example, its surface area, the surface area of, let's say, metal conductors on top of it, which introduce losses, other things like the thickness of the solar cell itself.
And the reporter, would you think that these two
would those affect it?
The loss, would they impact?
Okay. We have dependence on these parameters, slightly dependence, but we specially define linearity mode of our photodetectors, and this step it's very important. We have it's in start and beginning this presentation. no main pad errors about.
So again, like
surface.
going back to going to the relevant parameters in this case. I'd say, for example, maybe some of the more relevant parameters would be, let's say, the reflectivity of whatever material you're using. That might also come into it. So did you guys consider the reflectivity, or was that something that you just took into account once you experimentally measured your efficiencies? So if I shine some light on top of a solar cell, some of it was
Time.
reflected back. Yeah.
Chemical configuration of detectors is very important because it is part of energy. It's different valence range you can see and different normalized different high of energy detected on this.
Now it's time for the jury questions. We'll start back from there. So,
What is the best method?
On different people, you can choose different methods on your taste.
For you, which one is the best? For you?
For me, the third method because I conducted these experiments. Also, I have two methods already, but these methods is interesting because a couple of the detectors and also we want make photodetectors yourself photodetectors on your hands with graphene in our lab and it's interesting topic. It's
Okay, can you please go back to the slide where you have all the temperatures close to the end? Where you compare the methods? Can you go to the slide? I just want to have a look on it. Close to the end, where you put the three methods and yeah, there. That
okay.
one. Oh, thank you. I just wanted to have a.
It's a frame on Planck's curves this data.
Okay. So those error estimations are related to the temperatures that are measured there by the.
The second method.
No, those are the temperature that you extracted from the method. Am I right? You extracted the temperature from that method in each case, and that's the error related to it.
I have these errors with our experimental data. These errors I calculated. I estimated and calculated formulas, equation in athletics. I saw.
No, it's fine. Okay, thank you.
Yes.
go ahead. Okay.
Okay, I have a question maybe for the opposite team.
Yeah, sure.
So we had a presentation about the solar cell responses, and we saw that the spectral responses are like varying because they depend on the length. Do you think it's the best methods to measure the temperature, for example?
So essentially coming up with an expression for the efficiency as a function of wavelength or frequency is quite a difficult task, and that is sort of what we did in this case. But there are certain approximations you can make. You can essentially go through, analyze case by case all of the losses that happen at the essentially when some light hits a solar cell, and identify where frequency or wavelength comes into it. With certain simplifications to that, and a little bit of numeric computations, I believe it is a viable method for calculating the color temperature. Essentially what it would be once you've got the efficiency curve, it would be sandwiched with the Planck function inside an integral, and you can numerically solve for it. It is not the most efficient way, but it is doable in this case, let's say. If that answers the question.
You're saying it's not the most efficient way.
Yes,
so
it is
you're
not the most
thinking
efficient
of a
way.
more efficient one?
Sorry?
You're thinking of
So the more efficient case in this case would be to try and measure the, try and measure the efficiency experimentally. So that's going about it essentially not knowing experimentally what the efficiency curve looks like, but calibrating it with a known with the black body. You should be able to solve it that way. Yes.
Maybe a question for reporter and opponent. So you talk about the difference between the effective temperature and the temperature of the black body, let's say.
Effective temperature, it's temperature with temperature of source, which have surface in theory of photosphere of stars. We have optical optical tau.
Okay, so the final numbers that you have are related to this effective temperature for the source?
I have effective temperature in the second method, I have radiation temperature in the third method, and I have color temperature in the first method.
Okay. Okay.
It's different.
Yeah. That's your question.
I have a quick question about the first method. At some point you used filters, and I just didn't understand how you choose the filters. I mean, you choose like a visual filter among several, and I just didn't understand that part.
I choose blue and visual filters with this selected wavelength because this wavelength using in photometric in astrophysics, photometric of stars, it's B minus V is power of color of star. It's parameter in astrophysics, and using in Gershwin-Russell diagram in calculated
The question was
explosion.
just that like, you tried several filter, like a V filter and another V filter, and you chose between them, right? So just
Two couples filter which cuts infrared range and filter blue, and filters cuts infrared range and filter visual.
okay, no, that's fine.
Yes,
Just a clarifying question from me. So you mentioned your photodetectors, and you had two graphs for gallium arsenide and silicon. Did I understand this correctly, that you used a photodetector with a different material than silicon?
You mean is that different materials and accuracy and different materials, because I won't get the same effect how in the first method, how with using light filters. Different wavelength range, I use how light filters. I use so different wavelength range, and I get ratio of voltage on these photodetectors, and I use approximation in MATLAB, and I get dependence on temperature in Planck's using Planck's law.
Okay.
Thank you all. So now it's time for the